Hello everyone. Today we are going to talk about fundamental simulation concept, especially using ARENA or discrete event simulation. Yes, let's look at the steps in a simulation study. First of all, you need to find the problem, right? So we are begin with the problem formulation, and then once we have a problem, definitely we need to set the object, and then also overall project plan. And then to meet the object and then project plan, yes, you can begin with developing a conceptual model so that you can actually understand the basic procedure associated with the subject system. And also you need to collect the data as well. And then once you have data and then conceptual model, then you are ready to develop the simulation model, right? And then so once you develop the simulation model, and then you need to check you need to verify the model. In other words, whether the model is functioning well or not. If there is any programming error, and then definitely you need to go back to your model and then develop the model again to fix an error, right? And if the model is verified, and definitely you need to check the validity of the model. So validation is slightly different from the verification, because in validation procedure you need to check whether your model actually mimic the characteristics in the real system or subject system. If your model cannot represent your subject system, and definitely you need to develop your model again. So you need to go back to your conceptual model first to understand the subject system functions or logic of the subject system very well. So that's why you need to go back to the conceptual model conceptualization process, and then you need to redevelop the conceptual model and then collect the data. And after that, you can just follow this procedure until you have validated model. Okay. All right. So yes. So when you check the validity of your model, yes, it can be also the problem is associated with the data collection. So if your data is not correct, and definitely you need to collect the data again, right, for your simulation study. And once you have validated model, and definitely you can use it to do the experiment, right? So in other words, to find alternative which can solve the subject problem, right? So definitely you need to design the experiment, and then based on your plan, and then you need to conduct the experiment. In other words, you need to run your simulation, right? And you will get the output of your simulation model, so that you are ready to analyze the result. Okay, if you need more simulation runs, and definitely you need to run the simulation multiple times, yes. Okay, and if you need to conduct the additional experiment, and definitely you need to change your experiment plan, so you can conduct the experiment again, right? So and then once you have enough result, and you can document your report. You document the result and then your thought, right? And then write the report so that other people can understand your solution, which can solve the subject problem. And although this is this procedure showing how you can solve certain problem using a simulation model, but you can also use this procedure to conduct any kind of research. Okay. And once you find the solution, and definitely you need to implement your alternative or your solution to the real system, right? And here is the modeling part, and here is the analysis part. So, okay. Let's look at the example of modeling. And let's say we have a real machining center which only has one machine. Yes, very simple model, but a simple system. And once you have this real machining center, and you need to develop the concept, you need to develop a conceptual model shown here. So in conceptual model, you don't need to really specify everything. The most important thing is that you need to have a server and queue, also a library procedure and departure process. Okay, so here is a drilling center. Okay, which is developed from this real machining center. And then, as you can see, we have one drill here, so you can have a one drill press here. Okay, and this is a server. We have one server, right? And so this drill press can process only one part at a time, and other part and definitely have to be in this queue, right? And each part following the interallable time between these parts, following the allowable process, right? And shown here also after the service, and the part will leave the system, right? And that's what you call departure process, right? Good. And once you have this kind of conceptual model, and you are ready to develop the simulation model, and using Arena, for example, and here is an example of the Arena. Basically, you don't know, and definitely you don't have to know about this procedure, these modules, because I will explain these modules in future. And however, the first one is just first module is used to define the allowable process of the part. Okay, process which will be processed by this drill press. And then here is a drilling center, as you can see. And then last one is a dispose module, which will represent the departure process in the real system. Okay, part departure. So basically, we have once you have a real system, and definitely you need to develop the conceptual model to develop the simulation model. That's what I want to say. And then definitely once you have a simulation model, you need to verify the model. In other words, you need to check whether this model has an error or not. And then also you need to check the validation of this model. In other words, you need to check whether this model really represents these characteristics or performance of this real system. Yes. Okay, let's talk about the sample path analysis, which was very popular in past. In other words, the computer actually came out when? It's only 1950s. Yes. So anyway, it was not really popular, right? I mean, it's like 50 years ago. So people widely use a sample path analysis as a simulation tool. So that's why I want to start with the sample path analysis. And sample path is a record of the time-dependent behavior of the system, as you can see. Sample path analysis is basically the analysis using this sample path. Yes, so in other words, sample path analysis is used to extract the system performances from by understanding the sample path. Okay. So here is an example of the sample path and simple process system shown before, right? Drilling center. And here we have a drilling center with the one drill press, as you can see, and one queue, FIFO, right? First in, first out queue. And so once you have this system, and we know that the part arrivals, right, over the time, and then once first part enters the system, and then definitely it will resolve the drill press, right? It will directly go to the drill press, right? So drill press can process a part and other part, while drill press processes the part. Other part entering the system definitely have to wait, right? Have to wait in the queue, as you can see. And then we have and then once process is finished, and then process part will leave the system, as you can see. So goal of this study is what? We want to measure the total production during 20 minutes. This is assumption, okay? Let's say we want to measure the total production during the 20 minutes, okay? And then also we want to know the utilization of the drill machine, also waiting time in a queue, and time in system. And also number of parts in the system and the queue. And here's the sample path, okay? So basically, it shows all the record of each part. Yes, all the record of the part. So here's initially we have first part, and second part, third part, fourth part, and so on. And then sample path consists of 3 elements such as arrival time, interval time, service time, shown here. Okay, yes, 4, yeah, including part number, right? And at time 0, part 1 enter the system, as you can see, and then service time, each service time is 2.9. Okay, and then interval time between the first part and second part is 1.73 minutes, which means after 1.73 minutes, second part will enter the system, as you can see, right? That's why arrival time of the second part is 1.73. Good. Yes, and also it will stay at the server. How long? Yeah, for 1.76 minutes. Yes, and then interval time between part 2 and part 3 is 1.35. Okay, so after this time, 1.73 plus 1.35 will give you 3.08, as you can see. So that part 3 will enter the system at 3.08 minutes. Now you understand, right? Now you can understand how this process goes. Okay. Right. So because we want to measure the other performances, so that's why you can actually expand the sample path. So now you can have a time in queue, time in system, departure time, and number of parts in the queue. Yes. Okay. And basically, based on these 3 parameters, you can actually calculate all these numbers. Believe it or not. So let's see. Time in the queue of the first part should be 0, right? Because there was no part in the server, right? At time 0. So that's why part 1 could resolve the server, right, directly, right, without waiting any time in the queue. So that's why time in the queue is 0 of the part 1, and then server service time is 2.9 minutes, right? So time in system is what? If you add this number to this, and then you will get the 2.9, right? And number of parts in the queue at this time is 0, right? There is no part in the queue. Time in system, yes. 2.9 plus 0 will give you 2.9, right? Because so this part was not in the queue at all, so that's why. And departure time after 2.9, because all the service will be finished, so that's why this part will leave the system at 2.9. Got it? Okay, and so calculation for the first part is very easy, but second one is slightly complicated. Let's look at this. So second part, arrival time of the second part is 1.73 because interval time between first part and second part is 1.73, right? I mentioned this before, right? So at this time, there was a part in the server, right? Part number 1 was in the server, so this one have to wait in the queue, right? So how long? Because it takes 2.90, right? The first part takes 2.9, So, and then second part arrive at the system 1.73. So you need to subtract this number from 2.9, right? And that value will be the time in queue for this second part, right? So 1.17 will be the time in the queue of the second part. And service time of the second part is already given, right? Based on the distribution, statistical distribution, which can determine the service time, right, of the server. So this is a given information, and this is also given information. Okay, and then all arrival time is calculated based on this interval time distribution, right? So anyway, right. So time in system. So number of part in the queue is 1, right? Because this part should be in the queue, right, at this moment. And then time in system will be what? Will be the summation between service time and time in queue, right? If you add this number to the here, and then you will get the 2.93. Good. And departure time will be what? 4.66, right? So you have to weight this number, right, to this value, right, service time to the departure time, so that you can get the 4.66. Once previous part leave the system, and definitely second part directly reserve the server. Okay. Okay. So in order to generate the sample path, you have to two things: input data and logic. Okay, and so that you can get the output from the sample path. And what kind of input data we need? We have to have arrival time, interval time, and service time. That's why we have these 3 columns, right, in the sample path analysis. And what kind of logic we need? And we have to have a recursive equation for the simple system or event mechanism. Okay, let's get to know about the components of the simulation model, especially discrete band simulation model. First, entities. Entity is a dynamic object in the simulation, and also entity is something moving through the system, and entity may not be tangible. Okay, it does not have to be tangible. It can be order for a company, and also the request and so on, or document. Although so if we look at the previous example, it was a tangible, right? It's a tangible part, which is processed by the drill press, right, at a drilling center. However, if you are looking at the service system processing the customer orders or document, and definitely that in that case the entity doesn't have to be tangible. It can be, right, invisible as well. Yes, so entities in this case is part. Okay, entities are part. All right, let's look at the attribute. An attribute is a local variable characterizing entities, and each entity can have same or different values. Third, entity values are tied to the specific entities. And values can be real number, integer number, text, or some other object types. For example, let's look at the part, okay, which was the entity at the drilling system, right? I mean, in the previous example, there was a drilling center, right? And then entity was a part, right? And attribute for this part can be part ID, arrival time, time in queue, time in system, and so on. So all the local variable associated with this certain entity can be the attribute. Got it? Yes. variables usually reflect some characteristic of the system, and these are the actually global variable used in the entire simulation software, and variable are not tied in specific entity, in other words, so rather pertain to the system at large. So that's why I personally call this variable as a global variable in Arena. Okay, and also this variable can be the system built-in variables. So system built-in variables in the Arena, for example T now, can be the one of the variables. Okay, so T now in Arena, if you type the T now in Arena, and definitely you can get the current simulation time. Okay, it's something like this. And user specified variable also can be the one type of variable. And next one is resources. The resources, usually resources are seized by entities or released by entities. So in the previous example, resource was what? Resource was a drill press. In other words, server or machine, drill press. Okay. And entities compete with each other for service from the resources. For example, personnel, equipment, or space in a storage area of limited size. That's why if you look at the previous example, where is it? Okay, previous example, and then this drill press can be the what? Can be resource. Can be a resource. Okay, so all these parts want to resolve this drill press, right? So we have drill press with one capacity, and this is a resource. We have one drill press, right? In the example, so that's why resources are seized or released by the entities. All right. And definitely the definition of resources can be different in different simulation packages. Okay, but let's just think about the Arena software. So once we have an entity here, parts, and we have a resource, which is a drill press. And next one, Q. So Q is just a place where entities can wait when no resource is available, right? In other words, waiting line, waiting space, okay? So you must model how to handle an entity arrival at a queue, right? That's already full. You have to revisit or delete it, right? So queue can be logical or physical, but in this class we usually use a physical queue, so physical waiting line to get the service. And this definition can be also different depending on the different simulation packages, but again, let's stick to the Arena. Alrighty, okay, so statistical accumulators. These are the variables needed for the storing statistical information. So as you know, we want to collect the performance. We want to estimate the performance of a certain system using simulation, right? So these accumulators are used to calculate those performance measures. Okay, and anyway, so these are used to estimate the desired performance measures. Oh, I mentioned it before, and such as mean time in system, okay, or number of entity in the queue, okay. Okay, so and also several simulation packages take care of statistical accumulation, and Arena is a very good tool to calculate the the performance measures of the certain system and using these statistical accumulators. And definitely using before we using Arena or other simulation tool, just we want to calculate the statistical accumulator by hand and using sample path analysis, and which will be very challenging. But yeah, you can do that. The next one is next one are event. Yes, and something that happens at the instance of time that might change the system state. Okay, so because we are dealing with what? Discrete event simulation, right? Discrete event, which means the event happened at a discrete time, right? So event means what? Event can be changed, event can change a state of the attribute, variable, or statistical accumulators. So event can be everything, okay? Which change the status of the system. So there are, however, in Arena there are 4 types of events, and one is initialization to set up things up, to set things up, and so initialization is the first type, and this makes the all zeros or initialization values. For example, statistical accumulator will be the 0 when we have this initialization event. And arrival event, next one is an arrival event, and as you know, a new part enter the system, right, over the time. That's our arrival event. And then departure event, so the finished part can leave the server, right, or the system, right? That's a departure event. The next one is the end event. So because a simulation has to be stopped, right? Has to be stopped at a certain time, right? So if you want to run the simulation for 20 minutes, and then that's a setup time, right? 20 minutes, and then at 20 minutes, simulation has to be stopped, right? So the end event happened when simulation is stopped. So at that moment, simulation actually calculate all performance measures based by utilizing the data in statistical accumulators. And you may wonder why not the following is not included in the event. For example, part leave the queue and begin the service at a machine, which change the system. Okay, so it can be the event, right? Because it changed the system. However, this is not the event. Why? Because this only happens when some other entities leave the system. So there was a departure event, right, of the other entity. So you don't have to double count it. Got it? In other words, we have departure event, right, of the part 1, and part 2 automatically reserve the server, right? So in other words, this event is triggered by what? Departure event of the previous entity. So we don't have to consider this as an event. Once again, we only have these 4 events in Arena, event types in Arena. Okay, so this is a very important one, and please remember these 4 types. Yes. Next one is event calendar, which is a place where the future events are stored. Yes, so basically it has a set of records associated with the following information. For example, ID of the entity, event time, event such as initialization, arrival, departure, or the end event. Okay, and event calendar is very important, right, to run the simulation model. In Arena, we have this kind of event calendar. Okay, so start from the top to the next, and we have initialization event, and at time 0, part 1 unlives the system. At 1.73, part 2 alive the system. At 2.9, part 1 leave the system. So arrival event, departure event, arrival event, and so on. And at the end, at time 20 minutes, we have the end event over here. Good. So this is a shape. This is an example of the event calendar used in Arena simulation package. Next one is simulation clock, because we run the simulation for a certain amount of time, right? For a certain amount of time. So that's why we need to have a clock which can check the current value of the simulation time, right? So we use a tnow. If you use a tnow function, built-in function in Arena, and therefore you can get the current time, current simulation time. Yes. And simulation does not take all values and flow continuously, because that's why we call discrete event simulation, right? And so when you run the simulation, you will just check the time when you have the event. So according to the first event calendar here, simulation will be start with time 0, but next time is what? 1.73. So there is no other times in between 0 and 1.73, because there was what? There was no event, right, at all. So you don't have to check anything here, right? So this will save a lot of computation. Yes, so simulation clock is updated when event occur. That's what I want to say. So event time of the top record from the event calendar becomes the current simulation time before the associated logic is performed. Okay? And stopping rule of the simulation. So time or number of parts produced. So you can use actually two options, either time. So if you want to run the simulation for 20 minutes, and definitely you can set up the 20 minutes as a simulation run time. Okay? Or you can also stop the simulation model by set the number of the parts produced. For example, if you want to stop the simulation when the system produces 100 parts, and then you can set the 100 as a simulation termination condition. Good? Yes. If a stopping rule is not properly given, simulation may run forever. Right? So basically you don't you have to have a stopping rule for your simulation model. Otherwise it will run forever, and then you cannot get any output because it will run forever. Okay? So which one is correct? Think about it. So one is a tnow is greater than 100. Next one is a tnow is equal to 100. Which one is correct? Answer is first one. So this is correct. Why? Because we are using discrete event simulation, right? So the time will be considered when there was event, right? Right? That's what I mentioned here. All right. Simulation clock is updated when event occur. So let's say event was occur at time tnow at 99 minutes. Okay, and then there was a next event at 101 minutes, which means tnow will be 99, and then it will become 101, right? So it will not consider the 100 at all. So next one cannot be used as a termination condition for the simulation model. Got it? So first one is the correct one. All right, so two types of statistics from simulation result. One is a tally statistics, next one is a time persistence statistics. And so tally statistics, also known as observation statistics, and time precision statistics are known as duration statistics. So tally statistics obtained from the observation of multiple entities. And for each entity, the starting point and the point of the data collection must be specified by the user. But ARENA automatically calculates the sum of tally statistics without specification from a user. So that's why we use ARENA. I mean, the ARENA will automatically calculate these statistics. That's a good thing, right? And for example, average timing system, average timing queue will be calculated in ARENA automatically. Here is one example of tally statistics which calculate the average waiting time of part in the queue. So as I mentioned before, tally statistic is associated performance of entities. So that's why once you have calculated the waiting time of all the parts starting from I to N, and then you need to divide the total waiting time by number of entity, which is N. Okay? So that you can calculate the average waiting time of the part in the queue. Right. And here's a logic to calculate this average waiting time of the part in the queue. And first, the simulation software create the attribute to record the waiting time of the part. So in the attribute, we have a time in the queue kind of option attribute in the part initially. So the waiting time information will be saved in this attribute. Okay. The name can be slightly different slightly different from the name using the ARENA, but for your understanding the concept of in order to make you understand the concept, yes, I just use this name. So time in the queue. Let's say we have a time in the queue attribute in an entity, which is a part. Okay, and then so WQI will be saved in this attribute. Okay. Next one, static accumulator update the total waiting time and also the number of entities left the system, which is N. And at the end of simulation, so when you have the end event, yes, so tally statistics, this average waiting time of the parts will be calculated. Got it? And time persistence statistics is slightly different from the tally statistic. It is a function of t, a function of time. It can be represented as a function of time. So these statistics are obtained from a trajectory of the system state over time. Okay, so and also these statistics these statistics do not have to be specified by user. In other words, these values will be automatically calculated. For example, machine utilization or resource utilization or number of customers in the system will be calculated automatically, so you don't have to worry about it. Okay. And then the time average number of parts waiting in the queue, for example, can be represented as this function. Okay, so because this is a time persistence statistic is a function of the time, so you have to use integration, okay, to calculate the statistic, right? As you know, by using this integral and then sign, and definitely you can calculate the area under the QT curve, right? Thinking of the basic math, okay, mathematics. And then once you have the total area, and then definitely you can divide the total area by t, which is a simulation runtime, so that you can get the time average number of the parts waiting in the queue, right? So if you have this kind of graph showing the number of showing the waiting time, number of parts in the queue at a time t, okay, then you can easily calculate this statistic. So here in this example, we have one entity at time 5, from time 5 to 13, right? And also there was two entities, yeah, sometimes between 7 to 10, right? 7 and 10. And also there was one entity in the queue from 14 to 20. Okay, so here's our library event and departure event, also another departure event, and here's a library event and the end event, because we run the simulation for 20 minutes. So that's why at time 20 we have the end event. Okay, and first entity arrived at the system at 3 minutes, but initially the server is empty, so there was no entity in the queue. And second entity arrived at the system at time 5, and however the server, one server, is already reserved by the first entity, so that's why we have this second entity have to stay in the queue, right? And the third entity also have to stay in the queue, so that's why we have two entities at time 7, right? However, there was a departure event, right? Which means first entity left the system at time 10, so that's why, and then that's why we have only one entity left in the queue, right? And then another departure event happened at time 13, so now we don't have any entities in the queue. Got it? And however, there is another arrival before the third entity left, so that's why we have one entity, which is entity 4 or part 4, will stay in the queue, right? So that's why we have this kind of shape, and by using this integral sign, we can calculate the total area, shaded area here, and also based on and then we can divide this shaded area by 20, right? Which is T, large capital T, right? So that you can calculate basically time average number of parts waiting in the queue. Good. All right. Let's talk about the event scheduling mechanism, particularly scheduling, which is to create a future event and placing it in the event calendar. Okay. And future events are created by the previous event in the arena. Okay. And as I mentioned before, by having a departure event, an entity can reserve the server, right? So something like that. So future events are created by the previous event. And in other words, the next part of arrival time is based on the arrival time of the previous part. Can you understand this? Let me go back a little bit. So if you're thinking about the sample path analysis, so initially sample path has a arrival time of the certain part, right? And then also service time for a certain part, right? Plus we have interval time, which is given by the interval time distribution, maybe Poisson or exponential distribution, which is widely used to determine the interval time between parts or entities, right? So number is given, and based on this number, we calculate the arrival time of the next part, right? So that's why next event, future event is determined based on the previous event, right? Let me go back to the slide. Okay. Where are you? Yeah, here you go. All right, so next part of lifetime is based on the lifetime of the previous part. Okay, and then the part time of the part is based on the time when the service started. I mentioned this. All right, anyway, so future events are created by the previous event. Good. And here's the event scheduling mechanism. So in the arena, we have main program. So initially, we have an initialization routine, right? Initialization routine has these functions. First is first set the simulation clock as 0, and then initialize the system state and statistical counters. In other words, make them 0 and initialize the event list. And next, invoke the timing routine. So we have a timing routine here, and timing routine determines the next event type. So say we can use I and advance the simulation time clock. So T now will be advanced, will be updated. And invoke the event routine. So update, whenever we have an event, we have to update the arena, not me. Yeah, arena has to update the system state, statistical counters, and also it should generate the future event and add the event list. Add to the event list. Good. Yeah, and then so main program repeat this in timing routine and event routine until the simulation end. So if simulation is over, and definitely the software will generate a report. So in order to generate a report, it has to compute the estimate of interest, in other words, proposed measures, and also write the report. So you can get the PDF file in the arena. So that's how event scheduling mechanism works. Yeah, it showed how event scheduling mechanism works. And then this is very important for you. So once you understand this mechanism, basically you are really ready to develop your own simulation model if you are really good at the programming. And other simulation software also follow this kind of mechanism. So that's why once you understand this mechanism, and definitely you can understand the logic of other simulation model too. Let's think about the sample path analysis to understand the event-driven hand simulation. Yes, and you can find the relevant content in the textbook. Okay, so let's look at this simple process system again, drilling center with the one drill press, and we have a living blank part procedure. Also, once part enters the system and drilling center, and definitely it will be processed by drill press. Okay, and then other part have to wait in the queue, as you know, right? And then there will be departing event as well once the part is serviced or processed. Okay, so basic nomenclature using this sample path analysis or event-driven hand simulation. So we have 5 columns. Okay, and then last column show you the event calendar. The first one is just finish the event, second one variables, and third one attribute, and next one static accumulators, and that's only in the arena, or if you want it, and then you can add more accumulators here, right, and so on. And the shop qt is the number of parts in the queue at a time t, and bt is the number of unit of the machines. The wq is the sum of the queue times that have been observed so far, and the sigma ts is the sum of total times in the system that have been observed so far. Yeah. Okay, so let's look at the initialization event or initialize event in this event-driven hand simulation. So initially, we need to the arena simulation software will set simulation time clock simulation clock to 0, as you know. So time becomes 0. Okay, and event type is so this is an entity number, and event type. So event type is the initialization. Okay, event. We have initialization event here at time 0, and as you know, an initialization, which means set all values 0, right? So qt becomes 0, bt becomes 0, and the waiting time and total time will be 0, right, in the system. And also initialize the event calendar here. So event, which means event calendar has entity number, time, and type. Okay, and if you look at this event calendar, we have a first entity arriving. This is the event type, right? Arriving at time 0. So this is the schedule of the first entity, as you can see, right, at time 0, right? And if we have the end event, and definitely you need the event calendar also has a end event at time 20, so 20 minutes, right? And then there is no entities, right, associated with this the end event, so there is no information about the entity ID. Okay, so arrival event happened at time 0, as you know, and arrival event, we have arrival event at time 0, right after the initialization event, right? So first entity enter the system arriving event at time 0, so Qt becomes 0, right? Because there was no entity in the system, so first entity can reserve the server, right? So that's why. And number VZ server becomes 1. Right. So, and then attribute in the queue in the server, an attribute of the first entity has a 0, right? And also we have another event, right? So event calendar has a next event, which is associated with the second part, right? So second part number 2, will be alive at the system, alive enter the system at 1.73. So we will have the updated sample path, in future. Anyway, okay. So anyway, when we have our library event updates the time purchase statistic and mark the arriving part with an attribute giving its time of the arriving. Okay, and in order to compute its flow time or the time it spends in the queue, right? If machine is idle, which means BT equals to 0, and then the parse goes right into service. I mentioned this before, right? And then the end of this service is scheduled at what? Arrival time plus service time. So arrival time was 0, and then here 0, and the service time of the first part was a 2.9. So the departure event, we will have a departure event at 2.9. Got it? So basically there was no waiting time for the first part. Yes, and then yes, this is the equation to get the 2.9 minute, and tally statistic is a part time in 0 time the queue, right? Yes, so tally this part time the queue 0, right? So basically the statistic accumulators will 0 because there was no there's no departure event. That's why. Next, yeah, when the machine is busy and basically the second entity enters the system, and then at 1.73, and then it will directly goes to the waiting line, right? So Qt value becomes 1 because the first server is already occupied by the first entity 1, right? So that's why it has to be in the queue. And then yes, and then there was a departure event. When you look at the event calendar, and then there is a departure event. Okay, when departure event happened, and basically it will increase the number of produced static accumulator and compute the flow time of the entity. So So by using this equation, so let's look at this departure event of the first entity at 2.9, and there is a departure event. So initially, there was a arrival event, right, at time 0, and then departure event at 2.9. And service time of the first entity is 2.9, right, in the server. So total time in service, time in system is 2.9 basically of the first entity. So when it leaves the system, so total service time, total time in system becomes 2.9. Got it? And also update the time persist statistic, because in order to update the time persist statistic here, so departure, when you have a departure event, basically we update the time persist statistic. So in this case, because the first entity already left the system, so BT value, number busy, becomes 0. Okay. All right. So departure event can be continuous. So when we have the second entity in the queue, and there is a the update of there is another update, right, in QT and BT. So QT is greater than or equal to 1, right? Basically, there was an entity in the queue. In other words, there was the entity 2 is in the queue, right? Was in the queue. And at 2.9, when the first entity leaves the system, the entity in the queue will reserve the server, right? Could reserve the server. So BT value becomes becomes 1, actually becomes 1, and then QT value becomes 0, right? And total time in the system is still 2.9 because only first entity left the system. However, the service time will be changed here, because this service time is what for the first entity. This service time is 0 for the second entity. However, this one is in the server, right? In the server, waiting time. This is the arrival time, right? Arrival time of the first entity was 0, and then this is arrival time of the second entity, right? So 1.73 is the arrival time of the second entity. That's why. So here also we have 1.73 because this is the arrival time of the what of the second entity, right? So this only show the arrival time of the entity in the queue and in the server, right? So that's why we have these numbers. However, most important part is the variables and also static accumulators. Right, and if Qt is just 0, then make the old machine idle. In other words, BT becomes 0. I showed this before, right? And when you have the end event, and at time 20 here, and it will just print out the total waiting time and then also the total time in the system. Okay, and then compute the final summary output performance and write the report. Okay, so here is a record of the hand simulation shown in the textbook, and here let's look at the overall procedure. At time 0 there was an initialization event, and at time so it will make all values 0, as you know, and variables are 0, and then statistical accumulator are 0, and type 1 there is a arrival event, right? So QT is 0, right, because the server is empty, so BT becomes 1, right, as you know, and then arrival time of the first entity in the server. In the server we have a first entity, right, and then its arrival time is 0, as you know, and sigma QT is still 0, sigma BT is 0, right, because 0 0 times 0 is 0, right, so that's why 0 0, and then also total time in the system is also 0 because there was no departure event so far. And next, there was a arrival event of the second entity, and then so Qt becomes 1 and BT becomes 1 still, right? And then arrival time of the second event is 1.73, and then arrival time of the first entity is 0.0, just a 0, right? And then other values are 0, but BG integration of the integral of the BT is 1.73. Why? Because the BT value has been 1 for 1.73, right? So 1 times 1.73 is 1.73, so that's why. And then total time in server system is 0. Next, there is a departure event at 2.9, and the first entity, when first entity leaves the system, the second entity will enter the server, right? And then this value will be nothing, and then so arrival time of the second entity in the server is 1.73, and now because first entity leaves the system, we have a value for the total time in system, right? 2.9 here, and 1.17 will be calculated. How? Because there was a Qt value for 1.17 time, right? If you subtract this value from 2.9, and then you will get the 1.17, right? So integration of the Qt will be 1.17, and then BT is 2.9, right? Because it's been 1 for 2.9 minutes. That's why 1 times 2.9 will give you 2.9. Okay, that's how you can update tally statistic as well as time persistence statistics. Okay, third one, there was a third entity arrival, right, at 3.08. So Qt becomes 1 again, and the BT is still 1, and 3.08 is the arrival time of the third entity. The 1.73 is the arrival time of the second entity, and 1.17 is still Qt value because it's been 0 for this amount of time, right? So this integration of Qt is still same. However, it's been busy. Server has been busy, right, for 3.08 minutes. So that's why this one is 3.08, and then the time, total time in system is still same, 2.9, because there was only one departure event. So tally statistic is only updated when we have a departure event, okay? Unlike a time persistence statistic, tally statistic is only updated when we have a departure event. Okay, so at the end, so we have this kind of number. Okay, if you look at the textbook, and you will have the same value. All right, so every number of part in the queue is calculated by this equation and time persistence statistic, right? So if you calculate the area, shaded area from this Qt graph, and then you will get the 15.78, and then divide this value by time t, simulation runtime, which is 20. So you will get the 0.79 parts as a value of this time persistence statistic. Good. And then machine utilization. So basically, it's calculated by this equation, and you can get 18.34 as the area of this shaded area, size of this shaded area, and then divide this value by 20, which is simulation runtime, right? We run the simulation model for 20, and then you will get the 0.92. That's how you calculate the two time persistence statistics.